Namaste from India, and a very good morning and a warm welcome to all the participants and our guest speaker, Dr. Tapas K. Das, for the fifth session of Enviro Web Talk 2021. Time is 9 a.m. according to Indian Standard Time, and I, Zutona Tuni, student of School of Civil Engineering at Lovely Professional University, will be your co-chair for the fifth session of Enviro Web Talk 2021. So, on behalf of School of Civil Engineering, Lovely Professional University, I welcome you, sir, Dr. Tapas K. Das, for your session on the topic Renewable Solid Waste to Energy Towards a Circular Economy. I am also thoroughly elated to introduce Dr. Amit Srivastava, Professor and Head of School of Civil Engineering, Lovely Professional University, who will be chairing this session and will be co-chaired by me and my faculty, Dr. P.K. Sharma. So to welcome the speaker on board, I now request my faculty member, Dr. P.K. Sharma, to kindly take over the session as chair and start the proceedings. Over to you, sir.
Thank you, Tunai. Uh, Namaste to all. It's my pleasure and honor to introduce and welcome Dr. Tapas Kedas to our audience who have joined us on this Google Meet platform. Dr. Tapas Kedas PE, BCE is a chemical and environmental engineer, a fellow member of American Institute of Chemical Engineers, AICHE, past chair of the AICHE's Environmental Division. He is a licensed professional engineer registered in the states of Washington and Wisconsin, board certified environmental engineer BCEE, and board of trustee with the American Academy of Environmental Engineers, life member of Indian Institute of Chemical Engineers, former senior environmental engineer at the Washington Department of Ecology as a visiting professor since 2005. Dr. Das has been teaching several undergraduate and graduate courses in civil, environmental, mechanical engineering, management programs at St. Martin's University, Washington. Formerly assistant professor in paper science and chemical engineering department and the College of Natural Resources at the University of Wisconsin at Stevens Point, and recipient of the Professor S.K. Sharma Medal and ChemCon Distinguished Speaker Award for 2007, given by the Development Organization for Sustainable Transformation, DOST. Indian Institute of Chemical Engineers and Service Award by the AICHE Environmental Division. Dr. Das obtained a BS in Chemical Engineering from Jadavpur University in Kolkata, India, and PhD from Bradford University, Bradford, England. Dr. Das was a postdoctoral fellow at the London's Imperial College of Science and Technology, a renowned college, and a visiting scientist at the Princeton University. He has wide practical theoretical experience in various areas, including air toxics and aerosols and particle sizing, advanced industrial wastewater treatment for water uh, reuse, solid waste management and combustion, profitable process, pollution prevention, reuse, recycle, redesign, environmental process, intensification, circular economy, life cycle process, or product design as a tool for innovation, industrial ecology, and eco-industrial park. Sustainable engineering and sustainability. Dr. Das is the author of two books, Industrial Environmental Management, Engineering and Science and Policy, first edition, John Wiley and Sons 2020, Towards Zero Discharge, Innovative Methodology and Technologies for Process Pollution Prevention, John Wiley and Sons 2005, and 16 book chapters and over 60 publications. Now I hand over the session to our guest to deliver talk on the topic renewable solid waste to energy towards a circular economy. There is an announcement for the audience. During the session, if you have question, you can put the same in the chat box, or you may ask at the end by unmuting yourself. Your questions will be taken care by the expert at the end. Till then, please keep yourself muted and your video should also be turned off. Thank you very much. So, welcome to Dr. Tapas Kedas. Please continue.
Thank you. Well, namaste to everyone. Good morning to everyone as well in India. I'd like to express my heartily thank you to Professor Sharma for his kind introduction. And I'd like to congratulate Professor Amit Sharma, Professor Amit Srivastava, and Professor Sharma, and all of your colleagues and students at the lovely professional university for organizing this such a broad-based environmental engineering seminar series particularly during this challenging time. What's happening, the pandemic and recent flooding and cyclone in India. So anyway, we are keep going, and I decided to talk about energy, which is very, very important part. All of us, we need energy. So we'll be talking about renewable energy sources. I would also like to thank all of you, particularly Professor Amit Srivastava, to invite me for your cordial invitation to participate at this webinar series. With that, I'll start my presentation. The first slides that you see, I'll repeat the title again, Renewable Solid Waste to Energy, Advancing Circular Economy. Okay. This is a case study done at a waste to energy facilities in the city of Spokane, which is located about 200 miles northeast of Seattle, right here, Seattle here, and Spokane is right across from west to east, about 200 miles, with a population of about 0.6 million in the metropolitan area. I live in Olympia, and the St. Martin University is right, it's about 4 miles from my house, which is Olympia is the capital of the state of Washington. Well, let's go straight into the objective of today's lecture and related topics. The present case study at the waste to energy facility in Spokane is about 800 tons per day municipal solid waste to energy that generates 25 megawatt per day of electricity, enough to power approximately 1,400 homes. This plant is a state-of-the-art plant that meets air quality standard, US Clean Air Act, US National Ambient Air Quality Standard, it's short called NAAQS, pollutants of concern, toxic air pollutants, best available control technology, in short called BACT, maximum achievable control technology for toxic gases, is in short called MACT, and the lowest achievable emission rate layer, and the health and the environmental effect. Okay. Then air separation technologies, we'll talk about particulate matters, in short PM control, that usually done with the cyclone and multiple cyclones, Baghouse or fabric filter, electrostatic precipitator, in short ESP, and Venturi scrubbers. And then the control of dioxins and furans, which is very toxic substances, and mercury by powdered activated carbon adsorption. And because the presence of chlorine, there will be some, and sulfur, there will be some acid gases, hydrochloric acid and sulfur oxides, which turns into sulfurous and sulfuric acid, primarily HCl and then sulfur dioxide or SOx, SO2 and SO3 by absorption. And then the electricity generation and then generating revenues for the city of Spokane. And the role of renewable waste to energy to advance circular economy. Then I'll conclude my conclusions and acknowledgement. So this first slide showing some of the densities of various municipal solid waste that we recover, typically newsprints, papers, plastics, cardboard, styrofoam, rubber, glass, bottles, aluminum, scraps, food waste, all of it. And the second column is the density, average density, and then you see the types of the waste on the right. Third column, and the density is the last column. They are in kg per cubic meter, SI units. And this particular table showing the physical chemical characteristics of those solid waste, that including food waste, magazine, papers, plastics, textile, rubber, leather, yard waste, and so on, glass and metals, woods. And then you have moisture content, which is very important for combustion. So we'll keep track of that. Energy values is also a very important parameter, chemical characteristics. Energy value after drying, moisture, carbon content, hydrogen, oxygen content, nitrogen, sulfur, and ash content. So those are all in table for each constituents, okay? Now we go into heat value, which is a major parameter for deciding to go into waste to energy. It has to have sufficient energy to recover to make energy to electricity. So the major consideration in this section or design of an incinerator or combustor is the fuel value of the materials being burned, right? So the fuel values are the gross, the higher heating value, HHV in short, and the low heating value, LHV. Now, American Society of Testing and Materials, ASTM in short, specify a procedure for measuring those gross heat value using a laboratory bomb calorimeter. I'm sure in India you have a very similar test procedures also. So for high heating values, we have an empirical relationship I quoted from a published book. So that's in BTU per pound. 145.7, that's times the carbon. The total carbon, which is also important to assess in the waste per kg, how much carbon molecules that you have, and then also hydrogen, 619 times hydrogen minus about 60, 59.8 oxygen plus 45.1 sulfur, okay, where C, H, O, and S are weight percentage of carbon, hydrogen, oxygen, and sulfur. So now we have to account for moisture. That was the dry format. So then we have to deduct the heat required to vaporize or the amount of moisture content it is. So we have hydrogen. In that equation, LHV will be HHV minus, this is the moisture content, W plus 9H. And the W is the mass or the weight of the moisture, okay? And H is the percentage weight of hydrogen because you need hydrogen, and oxygen will be water vaporized. And the average heating values generally calculated from various testing, and I'm reporting here about 10 to 15 megajoule per kg. This was again published in journals. Okay, So the two boilers that operates here at Spokane Waste to Energy facilities, two boilers feeding 800 tons per day mass burn. Okay, so 400 tons per each boilers. Steam turbine generates about 26 megawatt hour approximately, 150,000 megawatt per year, assuming it's operating almost 365 over the years. Revenue generating that varies seasonally depending on the demand of electricity for summer versus winter is about 38 megawatt hour to 48 megawatt hour. Okay. So here is the schematic of this municipal solid waste to energy facility. As you see the waste coming in, and then this going into the pits, and then the crane operator picks up and then feeding this the boiler incineration sites to the hopper, the hydraulic ram feeder, and then this is the boiler, and then the capture the fly ashes. And then the heat goes to make it's a wall. On the wall you have water walls, and the steam generates stored here in the steam generator, and then from there directly goes to the turbine generating electricity right here, and then the ashes, particulate matter, goes to fabric filter. In this case, they use fabric filter for particulate matter control, not electrostatic precipitators. There must be some cyclone separator as a pre-treatment to take all the big particulate matters. Some of them are chunks, still very hot. So in order to avoid any fire, typically cyclone will be a pre-treatment, remove all the big particles, and the finer one, relatively speaking, goes to the back filters. And then as the ash is collected here, through that goes to a collection system to the truck, and then trucks takes away away from the landfill or wherever that will be used, cement making and so on and so forth. So that's typical. And then the clean air from the baghouse that goes through the stack. This is the stack. Okay. Now, as you know, it is very important to have air for the combustion, and to have good combustion, good quality combustion. So stoichiometrically, we need to know how much carbon is present, nitrogen, either in the fuel. Of course, we have 78% nitrogen in air. So the temperature is very important to maintain, and also supplying air with an excess air. So this diagram shows if we are around this peak, anything below will be in complete combustion. That means the carbon monoxide will be present. So carbon not directly going to carbon dioxide. And any areas of here will have excess oxygen. It can vary 5 to 10%, typically, maybe not more than 5%. Otherwise, you'll demand more and more nitrogen oxides will also be produced. So this is a good section. So stoichiometrically, you had excess oxygen, you combustion and monitor carbon dioxide, temperature and oxygen content. That will ensure that combustion is taking place in completion. Okay. So that excess air, and how much excess? Okay, non-hydrocarbon in waste like sulfur dioxide, halogens, chlorine primarily, fluorine, bromine. The nitrogen, of course, you have some nitrogen in fuel, but rest the nitrogen is in the air. And some metals, iron, copper, zinc, maybe those, mercury could be, yes. So the fate of halogen will produce acid gases from this equation. Chlorine, typically you'll have some plastics and other, and paper because it's bleached. Nowadays, most of the paper maker don't use elemental chlorine because dioxins issue. But anyway, chlorine, there will be some, and then it will make hydrochloric acid based on this equation here. Then move on to the next, and this is the equation that will actually partial pressure of hydrochlorine, oxygen, and water that will give you the K values, and you can calculate what the optimum condition would be. The fate of sulfur, in this case, if you have sulfur in form of hydrogen sulfide, and that will burn, sulfur and sulfur dioxide will make sulfur dioxide and sulfur trioxide. If you have excess oxygen, so it will be further oxidation from SO2 to SO3, and that is SOx. Both SO2 and SO3 will make sulfurous acid and sulfuric acid as acid rain. We'll come back to that later on. Fate of nitrogen, you would have nitric oxide and nitrogen dioxide. Okay, and that we call in NOx. And fate of metal, most metals will be in vapor form, and they will be scavenged by the ash particle. And I have a slide to demonstrate that. Very interesting. And then some will volatile, it's like lead, iron, and then mercury too. Arsenic, antimony, cadmium, it depends on the electronic. If the electronic waste are there, then we might have some of those. Otherwise, copper, iron, mercury. We don't use bulb anymore that had mercury, but still, old thermometer, whatever, will have some mercury in the waste. So those will be in vapor, and they will be interacting with the ashes as they move along from the boiler in the cooler region. There, they will scavenge by the ash particle, and that time around 300, 320 dioxin will start forming, condensing all the carbon. Very interesting phenomena. I'll talk about null theory, how it happened at what conditions. So the importance of those incineration is 3T. I'm sure you know this. 3T is time, temperature, and turbulence. Temperature at least will be 1200 or even higher, between 1200 to 2500 Fahrenheit. That's the temperature. Time at least has to be greater than 2 seconds. And the turbulence that adjusts the flow and mass velocity to promote the mixing. That is very important also. So in mathematical sense, these 3 T's are related to 3 characteristics times: a residential time, T sub R, a mixing time, T sub M, and the chemical reaction, T sub C. And those can be expressed in terms of tau R, which is a velocity time volumetric flow rate, L by U, which will be time, seconds. Tm is a mixing time, which is L square length of the boiler, and the diffusion coefficient. So L square and the area by second, so that will be a second of the mixing time. And 1 up to C, K is your reaction rate constant, so 1 over K will give you second. So as I mentioned, V here is the reaction zone, meter cube. Q is the volumetric flow rate of the fuel as it comes in terms of cubic meter per second, length of the reaction zone, and then the solid gas fuel velocity in the incinerator. And then D sub E is the effective diffusion coefficient due to turbulence, and the m square per s. K is the reaction rate constant, 1 over s. Okay, so now let's go back to excess oxygen stoichiometric ratio based on this hydrocarbon C sub x and Hy. And then we know, according to this formula, the 4x plus y divided by 4 times oxygen molecule will be required, and that will make X amount of carbon dioxide plus Y by 2 amount of water vapor, assuming it's complete combustion and no carbon monoxide is actually producing. This kind of ideal situation. And then this would tell us the stoichiometric ratio, how much oxygen we need. So then add excess oxygen based on typical practice that best management practice we do in the industry. And those comes from their experience, and they get those right. It can depend everyday operations. This graph is also showing the actual air-fuel ratio and some of those pollutants like carbon monoxide. So you don't have to operate any of these areas. And then as you see, hydrocarbon increasing this way, and this is oxides of nitrogen. So basically around this length, your stoichiometry about 14.7 ratio, that is your good stoichiometric. So you'll operate here or this side, okay? And on this side, you have a hydrocarbon concentration, and this side you have parts per million nitric oxide production. Okay, so the best combustion practices for refuse-derived fuel are sub-RDF, quality with high BTU values and low moisture content, and expressing a primary and secondary air supply in the boiler, secondary to ensure complete combustion. And then the continuous emission monitoring system here is must in short call sense of carbon monoxide and oxygen and temperature. This operator monitoring all the time to ensure the complete combustion is taking place. There is no problem. If we have a certain amount of CO and level of oxygen low and temperature, that would indicate that not having complete good combustion. Well, this is the structure of dioxins and isomers furan. The difference is the furan has one less oxygen. So you have two benzene ring. In the middle, you have two oxygen atom. And if we take in clockwise the position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's the location. And when chlorine stick to this 2 and 3 position and 7 and 8, then the TCDD, which is tetrachlorodibenzoyl and that in terms of toxicity, research found out that this particular combination of chlorine's position makes the most toxic among all dioxins and furan isomers, okay? So that is something that we'll keep in mind and then De-Novo synthesis and Deacon reactions, actually two mechanisms that tell us how the actual dioxins form during this incineration process, okay? Let's start with the De-Novo synthesis. The dioxins are formed in the cooler region of the boiler flue gas as it moving away from the boiler, getting cooler, and then going to the control technology, where the condensation onto fly ash particulate can occur as they're condensating, and then coagulation, condensation, and condensation, coagulation. In that form, they could form benzene types of sulfur ring, and they can mix together some of the metal like iron and copper. They act as a catalyst and then form dioxins. So this next bullet says that PCDD or dioxins or furans are formed from all organic carbon sources and chlorine in the presence. You have to have chlorine. Very trace amount of chlorine is needed, not a whole lot. Presence of metal catalyst, as I mentioned, because municipal solid waste will have iron, copper, aluminum, or zinc. All of those will act as a catalyst. And they are in vapor form, so they'll form a coating on the ash particle, and then the dioxins will actually form. The chlorine will attach to it, and then other organic precursors like benzene, phenols also can do this same thing. The copper ions has a strong catalytic effect on the formation of dioxins and furans around this temperature. Right around this temperature when they're cooling, and that's where the research found out that dioxin, trace amount of dioxin started showing up in the gaseous form. And then lead, ferric, and lead and zinc, iron as a minor effect, as a catalyst. Additional significant effects are attributed to carbon source, the types of carbon, their morphology, percentage of oxygen, temperature, and then the aerosol and fly ash size distribution. And the next slide will actually show that in the Deacon reaction, is saying the process involves the oxidation of hydrochloric acid in the presence of a metal catalyst to produce chlorine and water. Chlorinated plastics, principally polyvinyl chloride, PVC, very much in use in piping and other components, are major source for chlorine and hydrochloric acid. According to these reactions, HCl, half of oxygen, will produce chlorine and water. And this reaction takes place around 900 or below 900 centigrade. Okay, now we're looking into the pathways and interaction of ash particles and other metallic species in the boiler, and the nucleation, condensation, and coagulation process. As is the high temperature, they're all in vapor form. And then you have a hydroxyl radical, maybe some of the metal oxides, all those are forming here. And the nucleation started forming at that temperature. This scale is the temperature scale, as you see, 1800 to 2000 Fahrenheit. And then the chlorination is also there. And then the metal hydroxyl ion, chlorine ion will be also combined. Metal chloride, as you see, particle size, the ashes are growing a little bit. And you get typically, sometimes you get the double hump, smaller hump, and then the bigger hump. In this case, as you see, 0.01 to 0.5 micron, very, very fine too, okay? So that typically happen in the post-boiler and while the mixed gas is cooling down. Okay, so here is another picture depicts the same phenomena. There you see this the smaller hump, small aerosol forming, and the larger one. Again, with the same, all the species condensating, and then temperature, around this temperature, you see this is happening. Again, solvent and metal dioxins, all interactions, and most of the metal, according to research, is scavenged by those ash particles. So you have enough ash particles and interaction, and that ensure very little or no actually in the exhaust gas. Okay. Now we are moving into actually historic improvement of ambient air quality. Typically, what we see over thousands of years, air quality has improved, and India is in the green light here. So, you know, some of the European American country air quality is pretty high. The number that tells you the improvement in air quality. Lower the number is better. And this is the year, and you see the continent here, Europe, North America, Asia, and Middle East, and so on. This was I obtained from Professor Bokshi at Ohio State University, and so I quoted his name, and he actually got it from Smith and other authors published in the Atmospheric Chemistry Physics. Okay, and so the next slide is actually showing the presence of dioxins, and once we actually inject powder activated carbon right around the boiler, when the hot gas is coming out from the boiler, that injection helps having additional surface area of of the particulate matter. So the absorption will take place. So the pre-control, you see the number for the total polychlorinated dioxins and furans, nanogram per meter cube at 7% oxygen. As you see, the pre-control, the numbers are high, post-control number is very, very, very low. And the relative efficiency, as you see, with the pack injection and amount, and also recent publications show that bromide iodine, if we inject a little bit of that, then the scavenging efficiency goes up over 97, 98% or 99%. Okay, so that's good news. So most of the dioxins or furan will be scavenged and they're locked into the surface of the ashes. Okay. And now we'll go back into looking to the National Ambient Air Quality Standard, in short called NAAQS in the US. These standards are established by US Environmental Protection Agency, and they have air quality radiation offices like, a very well-known research facility center in North Carolina, and they do a lot of research related to air quality. So what I see on the left have pollutants, first carbon monoxide, and then nitrogen dioxide, ozone, particulate matter, 10, less than 10 or 10, and then the secondary aerosol that form in the atmosphere, particulate matter 2.5. And so the carbon monoxide has national standard, two standard, primary and secondary. Primary to protect our health, human health, secondary to protect the environmental health, trees and others, animals. So got two short and long, 8-hour average carbon monoxide in the busy area, a lot of traffic, you will have 1 hour average. The monitor are placed in certain area, and then they measure those, and those data goes electronically to EPA's offices. So the primary for 8 hours is 9 parts per million. It is the same as the secondary. And then the 1 hour average is also same for both primary and secondary, 35 millimeter. For the state of Washington, sometimes the state can be more stringent than the national, but in this case, Washington state has the same level. For lead, we don't have lead in gasoline anymore in the US. So still then the lead is monitored quarterly average, and that's about 1.5 microgram per meter cube. And there is no standard for the state of Washington. Then ozone annual average, you see 53 parts per million or parts per billion, 53. And then the Washington state has 50 parts per billion. 1 hour average, 120 parts per billion. 8 hour average is 75 parts per billion. Particulate matter at 10 diameter is annual arithmetic average 50 microgram per cubic meter, and that's also 50 microgram per cubic meter. And so the state is the same. 24-hour average is about 150 microgram. This is the annual arithmetic mean, which is much lower. For daily average will be 150. Anything exceeding that number means that they're not meeting the standard for that particular day. Particulate matter 2.5 is about annual arithmetic mean is 15, and then 15 and 35. Next, go to sulfur dioxide that has a 3 average, 24-hour average, 3-hour average, 1 hour average, and you see all these numbers. And here, 1 hour average, they do not have standard, used to have standard, but the state has some mills that produce sulfur dioxide, so they have 0.4, Washington state has that number. Lead, as I mentioned earlier, it is an annual 0.15. And the total suspended particle, TS, total suspended particle annual mean is no standard, and then the Washington state has 60, and 150 micrograms. So anyway, so the National Ambient Air Quality Standard is summarized here. So I'll move on to the ash generation, utilization, and disposal. Total from this facility annually, 76,000 ton annually, lot of ashes, about 25% of the total weight of the processed municipal solid waste. So a lot of ashes, but there are beneficial use of ashes. I'll come back. Most fly ash is used in concrete or cement manufacturing. Remaining ash goes into a landfill. The process municipal solid waste volume is reduced by burning it by 90% volume, which is great. Next, look at some of the health effect. As we know, the COVID also doing havoc similar way. Our lungs that has very fine capillaries, alveoli, alveolar. So when have fine particulate that doesn't really screen our nasal system, so it goes straight to the lungs, and through those fine capillaries, some of them get stuck, and some of them may carry some toxic substances that could release eventually in the systems, from the blood to our cell. So that is important to remind us that fine particulate matter could be a very health hazard. So removing as most fine particulate is possible. That is a great idea. And as you can see here, oxygen being transferred, and then we exhale CO2. So any blockage in the lungs, you will not be able to uptake oxygen from the air. So now moving into particulate matter control, looking at the cyclone separator. In cyclone, particulate matter enters with the gas are removed by centrifugal forces because the particle have more momentum and cannot turn with the gas. The air is moving in a helical pattern, as you see in the picture, and then the particulate matter, they momentarily hammered on the wall, and then by gravity they fall down, and that's how we separate particulate matter laden in the air. Dirty air goes in there, and the clean water goes out, and the particulate matter is actually comes from the bottom. So that's cyclone. And if you use more than one, then we call it multi-cyclone. It depends the amount of volume that we are processing. High pressure, but very fine particulate matter, not able to, particularly those are greater than 10 micron, less than 10 micron, that goes to the air, and that we need a separate second control technology. Typically, baghouse are used for incineration. And here is the baghouse, a series of bags that goes to the dirty air, comes from here, goes to the center of the bag and capture all the particulate matter, and the clean air goes out, and that goes out through all these bags. Again, the number of bags and the cloth area required depending on the volumetric flow rate that we're handling. And here is the equation here, gas to cloth ratio, that cubic feet per minute divided by the total cloth area is a square feet for fabric filter. For electrostatic precipitator, the particulate matter has to be able to carry a certain percentage of charges. Otherwise, you won't be able to use electrostatic precipitator. That is one of the reasons typical incineration ashes are insular and they don't use electrostatic precipitator. The principle, how it works, the gas particulate matter laden going through these plates, and you have a metal, fine pointing metal that carrying high charge will produce corona. You'll see light blue color corona, and then the gases, as is passed through, the corona will charge them positive and negatively, and then that will be attracted by the plate. We maintain a positive charge and will be attracted towards that charge, and that how you separate the particulate matter by charging in the electrostatic precipitator. There are two types, and now we have a dry and wet. We have wet. So if you have a fine spray, goes along with that, and that will actually take care of all the particulate matter that actually stuck on the wall, and it will actually make a kind of a coagulate together. It will be easy to remove that way. And if it is a dry one, there is a wrapper, which is a hammer. Basically, it will hammer and will dislodge those particulate matter. And I forgot to mention, in the air bag filter, there are some injection of high air periodically, which is programmed, and that will blow from the outside, and that will dislodge all the particulate matter inside, and that way the cloth will have no coating of particulate matter. Pressure drop will be reduced. That's for fabric filter. And here we are doing kind of same thing with the dry, just removing, shaking it, and removing the particulate matter. And that way the surface will active more efficiently. So that's pretty much control for particulate matter. And you see the ESP, the efficiency, collection efficiency, as you see, finer particulate matter, 0.5 micron, that has no more than 75%, but anything between 1 and 10, you see around 10, you have almost 100% removal efficiency for ESP. ESP typically more expensive to buy, capital in as well as operating, because high electricity. Fabric filter, you need fan, and the filter is much cheaper. You have to replace every now and then. But overall, fabric filter in terms of capital as well as maintenance operation is less than ESP. Okay, then the Venturi Scrubber. Again, Venturi Scrubber have advantage that in addition to particulate matter, it can remove sulfur dioxide and hydrochloric acid because it's water-based. Its efficiency is less for fine particulate matter. So not many industry will actually adopt the Venturi Scrubber. But as I mentioned, it has you can kill 3 birds in one operation, because it could remove sulfur dioxide, acid gases as well. Fabric filter has the ability to remove acid gases, which I forgot, because the coating you will have, those acid gases will be blocked. They are typically calcite based, so that will be blocked, and they're not going to move outside the bag. And there will be pH issues, but corrugation issues, but that also works. But for ESP, acid gases really doesn't work very well. Here is an interesting table of the cost effectiveness, dollar per ton. Now we have 4 technologies to remove particulate matter. How much is going to cost, the operating cost, capital cost altogether, total cost accounting against the flow rate. And as you see, as the flow rate goes beyond, the cost really comes down. For a larger system that is greater than, like 300, 400,000 dry standard cubic meter flow rate, your cost per ton goes below $200. And I shown calculation in my 2020 books for different flow rate, for different control system, how much it's going to cost to remove a ton of particulate matter. Sulfur dioxide, again, SOx. These are the equations. You make sulfur dioxide, trioxide, sulfate ion. And so there's 3 equations shown. And thermal NOx, there are 2 types of NOx are formed. One is the thermal NOx, the oxygen you have in the air if you use air. So that thermal NOx at the high temperature, thermal NOx will be formed according to Zeldovich equation that shows NO1 for these 2 equations. And then if you have nitrogen, in the fuel, that will be fuel-bound nitrogen, but that are smaller compared to thermal NOx. In order to control thermal NOx, the temperature is definitely important, and excess air and amount of nitrogen. Those two are variable. It is a very delicate managing that the NOx formation. And nitrogen content most municipal solid waste is up to 4%. And also not having too excess air, that could also reduce the NO formation, nitric oxide formation. Okay, and the removal, the two technologies are popular in the US. It's called selective reduction and non-selective reduction, SCR and SNCR. SCR operate at lower temperature because you have vanadium oxide or tungsten oxide, those kind of catalysts, very expensive. And you see 300 to 400 degree in presence of ammonia injection, anhydrous injection, ammonia, and that reduces NOx with the ammonia, nitrogen gas, and water, basically. The difference between selective and non-selective, you have to operate at higher temperature. It will cost you a little more, but you don't need catalyst. And catalyst poisoning is also an issue for that. So this is about 900 to 1,000 degrees Celsius that you have to operate in order to get this total reaction and then have clean nitrogen and clean oxygen. And then weight absorption, there are certain chemical, they will absorb NOx. That number of papers been published. And absorption, there are certain solvent will actually absorb, like this ash particle we saw, will actually selectively absorb the NOx. That's less expensive technology, but it has some limitation. So now we're moving into this circular economy, from linear to circular. In the linear economy, what we've been doing, we produce, use, we make, use, and discard. Okay, and that's the linear economy. The circular economy, we are talking about reuse, repair, remanufacture. All those things are involved. In this particular case, municipal solid waste come back. So the difference between the circular economy, we're using the same materials after use. We recover, collect, reuse, just like an aluminum can, glasses is good examples, and many others. So this is the linear, this graph showing the linear and circular economy. So the pathways to circular economy, the current circular economy involves a complex approach to economic activity, multiple use of material resources achieved through implementation of respective technologies and organizational innovation of production processes and waste management scheme. Such an approach leads to a significant reduction of the virgin raw materials. Like you don't have to use a lot of trees to cutting down the paper. If you could recycle and collect the fiber from the paper, and you could again reuse. And nowadays we mix with the recycled fiber with the virgin fibers. So that same idea, metal consumption, aluminum is great examples and doing extremely well, recovering and reusing. Of course, you have to remove the ink and other things. To spend energy, you're not getting straight in order to make it again a fresh resource to make the can, whatnot. So that's increasing these renewable resources and demanding for fresh materials mining will definitely be improved. Okay. So that's the pathways to circular economy. More times you reuse, recycle, the circular economy gets better, and you get the most return out of that. This is a formula was made, and the new showing the circularity matrix R sub I and Q sub I divided by R and Q, why new is the selectivity circularity matrix. Q is the non-monetary values of the product. In this case, municipal solid waste. how much a ton will cost. The facility they have to buy from the city, whoever supplying, and so how much is cost per ton. The grocery plastic bag per unit. R is the mass of the refuse-derived fuel in this case. QI is the quality indicator. I'll come back. This is more applicable for if you have to do something to prepare the recovered material in order to be ready to feed for the recovery process. So that depends. That could vary from 0 to 1 ratio. Ri is the quantity of the mass and the energy of the ith flow. If it is more than 0 flow, I could be 1 to 3. Say for aluminum, it could go high number. For paper, can go high number. So that will be that number has to be included into that. And so this equation will tell you actually your circularity matrix. Higher the number is better. If the flow goes to landfill, the QI may be 0, but you are making methane, so you'll recover some of that. So it's not exactly 0, it will be partially, it will be less values. And that is, it depends on how much methane is generating per ton of solid waste, okay? And here is the logo that we are all familiar, that reuse, recycle, and it's part of the circular economy. The waste to energy process can play a role model in the transition to a circular economy, while the waste hierarchy is used as a guiding principle that choices made to not prevent higher level of prevention, reuse, recycling. All those things have to be practiced first, then it goes into waste and then recovering. Okay, so that's first part. And then the second part is on the other hand, one may argue that waste to energy can encourage wastefulness. That means you're not practicing recovery, reuse, those good things, and discouraging recycling to ensure regular feedstock are available to incinerator, which could further contribute to air pollution problem due to released toxins and greenhouse gases we mentioned earlier. So that is what to keep in mind. And there's a table, sorry about the font, that table is actually showing some of the pros and cons of the two methods. Historically, we've been using landfill for many years. US has a lot of lands. So like Japan, unlike Japan and other country, they go straight incineration from the beginning. But US, a lot of landfills still are in operation and waste to energy. So these two tables actually compare the pros and cons between those two process managing the municipal solid waste. Okay, and the references, I'm using my two books primarily, and 2020 has an appendix that has pretty much this waste to energy case study. And then 2005 book Towards Zero Discharge has a solid waste chapter. In there we talked about use, reuse, recycling, all types of, and there is a case study of plastic and paper recovery in Bangladesh. And in page 545 to 596, and that chapter was written by Professor Nigel Bell at Imperial College London, and one of his students, Dr. Mia, I think he was from Bangladesh, and so I invited them to participate in that particular section. So with that, let's use a conclusion. These are the cover page of the 2020 books. That's Industrial Environmental Management. And when I was teaching at Wisconsin, I found out there is no reference book available, never mind textbook. So after I returned in Washington and started teaching at St. Martin's, I decided to write a book, a textbook on this chapter. So it took 3 years or so. So it published last year in March, I believe. And this is the 2005 book, and it's a 13-chapter book. It's a very good resource. Jadavpur University Library has a copy, and Chemical Engineering Library also has a copy. And I gave one copy last time, 2019, to Vice Chancellor, Professor Siranjit Das. And so that's still a lot of useful information in both books. So let me conclude. The main aim here at the City of Spoken Waste to Energy facilities to reduce the amount of waste generated, thereby reducing the need for landfill space, and also extracting maximum value from the waste, and thereby creating revenue for the city and local jobs as part of the consumption, recover, reuse, use, and that are integrated into the circular economy. And waste-to-energy plants are designed to reduce the emission of air pollutants using various pollution control technology. We talked about it. Also, with high temperature efficient combustion operation in excess oxygen, environment significantly reduce the dioxins and other pollution formation. Waste-to-energy aspects are becoming more prominent due to rapid depletion of natural resources and increasing in waste generation. Like developing country like India, we're using a lot of packaged materials, so that's also generating. So segregating, recovering that, and use that as a resource to burn and extract energy, and that's the way to go. In 2019, I actually gave exactly similar presentation at a conference held in the Bhubaneswar, Kalinga University campus, beautiful campus. And that was the first week or middle of November. And that was a good, and that was my first trip to Bhubaneswar. And I encouraged that this technology is a really state-of-the-art technology, and India should actually think about implement this kind of technology. So as I mentioned, this also play a role in transition to circular economy, where the waste hierarchy must be used as a guiding principle to ensure prevention, reuse, recycling are not averted or avoided. Okay, I'd like to acknowledge a great help from the superintendent, Mr. Christopher Everett, at the Waste to Energy Facility Spokane, gave a wealth of information, and then my personal and the personnel at the City of Spokane office who actually in charge of this plant. And then the Washington Department of Ecology's solid waste and air quality program. I got some information and data from them. Right here is about 4 miles from my house, the headquarters. And of course, the U.S. Environmental Protection Agency's Air and Radiation Office in Research Triangle Park in North Carolina. And my senior graduate students, and I gave them a design project based on the solid waste to energy facility, and from their report and some of the work they have done. So I also acknowledge them. Thank you very much for your attention. Any question, I'll be happy to answer.
So really very informative and amazing. Thank you very much, sir, for giving an insight of the issue, and I was really amazed to see few points you addressed so well in your session. One, the solid waste conversion to energy, and especially you coined a word, circular economy, that will undoubtedly open new doors for budding researchers. And many air separation technologies with mathematical evaluation, mathematical formulae for SOx, NOx, SPM, RSPM separation to improve the air quality, and various air quality standards to highlight. And one more very important thing, Deacon reaction, you explained very well, and that will be helpful to decompose, I think, polyvinyl chloride products, plastic products for budding researchers. And one more very important thing you explained is scrubbers. These scrubbers are very useful for the air separation techniques, but the natural scrubber that we people have, our nose nasal system, nowadays it is failing. What I think during COVID-19, you could have explained this. So with these points, to hear from you, I'm sure our future researchers, scholars, and students must have been benefited. Now I request my co-chair to start the question answer session, please.
Okay, can I interrupt before maybe a question on that, but the last question about scrubber, one of the difficulties with the scrubber, although it takes remove particulate matter, although fine particulate efficiency removal is low, but along with that, if your acid gases percentage is pretty high, that makes sense. The problem is that when you have this wastewater laden with, mixed with particulate matter and other constituents, then you have to treat that. You just cannot dispose it to any place, and here they won't allow. So that's why the scrubber is not going to be easy technology, and of course you need water. It depends where you getting the water. If you take the fresh water, of course, every drops of water is important with 1.3 billion people, so taking groundwater is another issue. Thank you.
So regarding this natural scrubber, our nasal system, I would like to have one question, please, if you have time. Should we use this wet mask for this COVID-19 or dry mask?
Well, just a week, 2 weeks ago, I put my mask all the way covering my nose. There is hardly no gaps on the top. I actually tie up the knots on the both ears.
Yes.
And make sure there is no air coming through. So breathing directly from the nose. So that means the fabric has to have pores. Typically, COVID, I think, is about 350 to 400 nanometers. Okay, very teeny tiny. So that means that cotton fabric, make sure not thin, not thick, so you can breathe comfortably, but at the same time, it will block anything around that fine particulate. So that's what I explained to my brother-in-law sisters back in Calcutta. And weight, definitely, but then how comfortable it will be wearing a mask. In India now, temperature is that is, I'm not sure. I never thought about it. That's a good idea. Okay. But anyway, that is critical. I think not having any space from the top, there may something can leak through or pass through. Anyway.
Yes. Thank you very much. Thank you very much.
Yeah, you are welcome.
Sir, indeed, we're receiving such good responses from the participants. Sir, you may now exit the presentation. You can click on the presentation once.
If I click on the site says end of slideshow, click to end, that will go back to the screen. I could see. Okay.
Yes, and you can exit it.
I can exit. Where is that exit button?
You can cross it. Yes, sir.
Oh, okay. Well, thank you very much. Yes.
No problem.
Now I can see some of you.
Yes. Now you can go to stop sharing. Yeah. Now you can go to stop sharing or stop presenting.
Oh, stop presenting. Oh, okay. All right. Very good.
Okay, sir. So now we will start with the question and answer session. I request the participants to put up their questions in the chat box if they have any. And sir, if you're ready, can I read out the first question?
Yes, please go ahead. Yeah, I'm sorry I took a little bit longer than the time schedule, but anyway, I have time. As long as you have time to have most questions, I'll be happy. I'll try to answer your questions. Go ahead, please.
So the first question is, in India, there is no efficient method for measuring dioxin. In that scenario, waste-to-energy plant, will it be effective? That's the first question, sir.
Okay, that is a very interesting question. Here only few companies, I know one in California, they will actually do analyze, in nano tetra level, 10 to the minus 12, 14 level dioxin, even they can see is just unbelievable, but very expensive. So I don't know, that's an issue. So that means we have to develop that technology. It is available, different parts of the world, Japan and many other countries, they have this technology in Europe. So India will just get that technology to how to analyze air sample, particularly looking for dioxins, not only just air, also ash particles that you will be able to leach and recover. And so all the procedure, I'm not sure. You can Google, Wikipedia might, but then again, that is the first thing. In order to have new technology, the new analytical expertise will be also required. And this dioxins furan analysis is very expensive. Did I answer my question, your question?
Yes, sir.
Okay,
So
thank you.
the next question is, can dioxin formation be decreased if incineration temperature is increased?
Well, that is an excellent question. Increasing temperature, it depends on the B2 values and how you operate, and that will cost you more to operate. But then, if you look into the De-Novo Synthesis, the main criteria according to the published research, in Rensselaer Polytechnic, there was an excellent paper I read that was many years ago. And 2005 actually have a review of that. So they said around that 300, 350 when the air is cooling as is moving out from the boiler, going towards a scrubber or other technologies, around that time it start condensing and the dioxins are formed. If you have, of course, you have to have trace amount of chlorine, and then the ash particle, typically those ash particle will scavenge most of it. And then a higher temperature means that it will shift the location where the dioxin will start forming. That's a very interesting questions and answer. I'm not highly sure about, but my good guess would be, depending on the, it's based on the De-Novo Synthesis during that window, temperature window, that's what the dioxin formation. If you operate at higher, because dioxins are not forming in the boiler, that would have definitely helped, but it's post-boiler. So higher temperatures means that we don't need that high temperature. Of course, then there is no CO formation, complete combustion, but then the overall energy efficiency, how much energy you put it into, extra energy, and how much you're recovering. So that is an issue also, energy balance and the cost.
Okay, sir.
Mhm.
That was a very helpful answer, sir.
Thank you very much. Go ahead.
Yes. So the last question for today is, what is the minimum energy content of solid waste for power generation, and how ash content of waste is affecting on energy value in addition to moisture content?
Well, I think, literature says here typically 415 megajoule per ton of waste. But again, remember the refuse-derived fuel, the one I used, RDF, which is selectively taking those materials that has BTU values, because the one that will be recovering from a household or businesses will have a lot of mixtures. Then we're going to discuss some of that, because if you have food waste, water, any water that you have to vaporize, and that will take a lot of heat from the combustion sources, that will be efficiency, thermodynamic efficiency will be low, and you don't want to do that. So basically dry, selectively taken papers, corrugated box and all that high BTU values, and make a refuse-derived fuel. And that has the highest BTU values. So that means that the sorting section, here in the US, one bin goes all dry stuff. We never put anything, the food waste or anything waste, so all dry stuff. So that goes to a special collection section. There, they will further depends, the machine will sort them out, and they will make they will collect the one that will go into feed into the municipal energy to waste plant, and that's probably the best way to do that, and having the maximum BTU value of your refuse. So there are some involved in the process involved, but each household is actually helping in the process. We take our bin once a week. In this case, in this area, Monday morning, they will come and pick up every week. And then every 2 weeks, all the paper, all the dry stuff they will collect. And then another week, they will take the bottles and cans and so on. Now, through office areas, school, colleges, they have the very similar collection systems. I'm sure in India, many parts, not all, have similar collection systems. So that's the way to go if you really able efficiently collect those high BTU waste values and then burn and extract energies, and having best control technology to remove pollutants. And that's the only way to do this process. And I'm sure this is the future of India or other developing countries. And that will save a lot of our resources. Our plant cannot provide all the resources. Our population is growing. We have the same amount of land, and we're taking away trees, deforestation, all those problems. So use, reuse, recycling is the mantra now. As best we could do, as more we do, better off we'll be. I hope I answered your question.
Yes, exactly, sir. So now we'll proceed with the ending. Thank you very much, sir, for taking up the queries of our audience brilliantly. On behalf of School of Civil Engineering, lovely professional university, and from the entire team of faculty members and students, I'm very grateful to you, sir, for sparing your valuable time and sharing your expert opinions with us. We wish you all the good health and a very prosperous life ahead, sir. Also, as a token, yes, sir. As a token of appreciation, sir, please accept our e-certificate of appreciation.
Thank you so very much. Yes, I see that. It was very nice of you. I wish you all the best in your endeavor, academic as well as in your profession. Those professors, Professor Sharma and Srivastava, they're so wonderful. You'll be lucky to have those faculty in your the school at the lovely professional university. Well, in future, if I'm in India, of course, I would love to go and visit you on campus someday. Thank you, good health, and wish you all the very best. Thank you.
Thank you so much, sir, once again.
Thank you, sir. Thank you. Thank you.
Please stay safe, sir.
Thank you very much.
Thank you very much.
I look forward to joining others webinars. I might see you again. Here is the Thomas. So it's good to see you on the screen. And I look forward. Yesterday I attended two till 2:30 in the morning, and I need a little bit sleep tonight. But then I'll be selectively watching, reviewing some of the webinars. You have an excellent program. Okay.
Have a great night. Good night.
Thank you very much. You too. Thank you very much. Have a wonderful day. Bye.
Thank you. Bye, sir. Bye.
Bye.
Yeah.